Okay. So it was just about a month ago that I spoke here where we were discussing not only the whole role of the Curiosity rover and this issue of asteroid defense. And I'm going to continue that discussion. And one thing that I just want to start with is everything that we've discussed about the space program, that is one flank. That is an important flank in terms of presenting to the American people and everyone else that there is something else we could be doing. And it's when I sit here and listen to Diane's briefing, and then I'm thinking about, well, how am I going to present this stuff on space? I mean, it's like this is from a completely different world. And literally it is. And also cognitively it is, because you immediately are thinking about what is possible. If we were completely unfettered by any of these, miserable problems and difficulties, what mankind could be doing and what we should be doing. And so that in and of itself forces you to think about the whole situation from a completely different standpoint, as if you were standing on Mars. So that, from a conceptual standpoint, makes this a very valuable discussion. Now, the thing that I want to start with, this just compares the different rovers that we've put on Mars, and how they had to send these technicians up there to fix something. I forget what it was, but they had to go up there. They had to make a service call. Now, what I actually wanted to start with, this is an editorial that appeared in Life magazine on June 15th, 1962. When I spoke last month, I played a section of John F. Kennedy's speech at Rice University, which was in September of '62. So this is 3 months prior to that speech, but certainly after Kennedy had already announced the commitment to land a man on the moon before the end of the decade. And this, I think, gives you a sense that there was an understanding of what we have called a science driver in economics. And in the course of the discussion we're going to have today, you're going to hear a number of concepts that Lynn has talked about literally for decades that are not only central to the question of space exploration, defense against asteroids, but the terrestrial economy. And in particular, this talks about the new economy, this mammoth new U.S. industry growing so fast it's already facing an acute labor shortage. They're talking about the space industry, the space economy. And they talk about how the budget is increasing and how this is creating tremendous demand for whole new industries. Huntsville, Alabama was building new schools at a rate of 1 classroom per week for the previous 7 years, which takes you back into the 50s, back to the time of Sputnik, when the United States recognized that we were going to have to make a major commitment to increase science and engineering education to address that in whatever form that took. Now, the thing I particularly want to focus on is this last paragraph, where he says that, the editors say that that we'll need to have all of the different components of the economy working together in order to accomplish this. In any case, other stimuli or cyclical pep pills will be the least of our needs these next 10 years. To take space in our stride, we will need the most mobile, slimmed down, competitive, and efficient economy we have ever had. And he describes a few of the necessary attributes of that. And then they conclude there will be no room, there is none now, for sloppy fiscal policy or carelessness with any of our resources. We'll need all those resources. That this is this idea of a science driver, of an objective which may have a fairly specific objective, placing a man on the moon, which is going to draw in every resource available to us to accomplish that goal in ways that we can only provisionally understand at the outset, but that we're going to have to create whole new industries. We're going to have to create all sorts of new materials, encounter problems that we can't even foresee yet. And that mission will pull the whole economy, not just into participation of that specific goal, but will create a whole new generation of scientifically educated citizens, people who, through their personal lives, have engaged in something profound. It's like if people think about, the World War II generation, people who participated in defeating fascism, they could rightly say, I did something important with my life. Now, that may be in sort of a negative fashion, but the very same idea, I helped to put a man on the moon. I participated in eliminating famine from the so-called developing part of the world. My life meant something. And that's the only hope we have to turn the sort of apathetic, self-centered, reality TV-driven population into a population that's willing to take responsibility for what the hell is happening to us.
They actually accomplished that. They counted that generation down to the ground. It's last 4 or 5 administrations.
Yeah. And so the issue of how do we create that? How do we take advantage of this crisis? Because this is actually a tremendous opportunity. We can bemoan all the problems and the danger of thermonuclear war. We can bemoan all those problems. But you better believe that is going to shake people to their roots. And in that kind of a crisis where people are rightly saying, what the heck is happening? I don't know what to do. I thought if I got an education, I could get a job, I could, it's all, nothing makes sense. That's not an answer, but it's a healthy state of mind. So that it creates the potential to get inside people and change them in a way that you couldn't when they were relatively comfortable. So this is from '62, and this is what enabled us to put a man on the moon and represented really the last positive impulse in our economy. So the idea of recreating that is really critical to give people a sense, and this doesn't simply mean putting a rover on Mars, but NWAPA, all of the things that we've discussed, all have that same sort of effect, and will all be critical parts of the space program, the strategic defense of the Earth, etc. All right, now, since I was here last, 3 very important things have happened in terms of our efforts to promote this program. First, wait, before I do that, I did want to give a short Mars update. And first of all, I'm glad that everybody was able to get up so early in the morning to come to this meeting, because this is essentially the dawn of Sol 47. Okay? That this is the 47th day of the mission of the Mars Science rover. And they have made some progress. And I'll show you the This is a picture taken from orbit about, I guess I would say, about 4 sols ago, which shows how far the rover has traveled, because it has started moving. Bradbury is the name they gave to the landing site, where it literally dropped out of the sky. And they have progressed to about this point, which is Glen Elg is the area where they are the immediate target in terms of some very interesting different geological types of soil that they want to investigate. And that what they've done along the way is that they have pretty much completed the testing and calibration of all of the instruments on the rover. They've determined it can move, all the different components of the rover are working essentially at 100%. They've had to calibrate all of the instruments. Just recall that this did go through the incredible vibration of a rocket launch from Earth, then traveling through space at, I don't know how many degrees above absolute zero for 8.5 months to get to Mars, then to survive the entry into the atmosphere, the descent and landing. And now it's operating in an environment unlike any of the testing labs on Earth where it was designed and built. So for example, when you extend this 7-foot arm off the front of the rover, it's operating in gravity about 38% that of Earth. So when you tell it, go to this precise location and angle, you have to recalibrate where the arm actually wound up, because the sag due to gravity is going to be different. All of these things will be slightly different. So they've completed the testing of all of these instruments, and they've also selected a rock pretty much in this area, named after a gentleman, Jake Matijevich, who was the chief surface operations engineer for this rover, who died 2 weeks after the rover landed on Mars. And he was a key engineer for the earlier rovers as well. So he's somebody who really had given his life to this program. And so the first rock that they're what they call contact science, where you actually reach out with the arm and touch it and do things with the instruments on the end of the robotic arm, they named it after him. And I'll just show you if I can make that a little bigger. This is sort of the business arm of the arm, the 7-foot arm, which can be deployed to touch and manipulate things on the ground. This is a sort of a magnifying glass that they can use to make very close-up microscopic examinations. I think this can remove dust from surfaces. The drill is over here. Once they probably won't use this on this specific rock. They may wait till they get to this Glen Elg location. But there's a drill which can actually grind up the rock, and then it can be scooped up and put into the little chemistry lab. This is just sort of a schematic of the same thing. This is the drill here. This is the part of the machine that will actually pick up and put material into the chemical analysis, a spectrometer. This is this hand lens imager. This is the chemistry lab. And it's kind of complicated if you just sort of looking at this. There are a million little tubes and wires and whatnot where they're going to put these samples, these small samples of dust or soil, and heat them to very high temperatures and see what sort of chemicals are given off. So, and these are on the sort of on the deck of the rover. That's where you'll dump the material in to be analyzed. Now, the other thing that the rover did this week was it did a little astronomy of its own. And these are pictures taken of the sun from Mars. And any idea what these little cuts?
It's the ellipse of Phobos.
Yeah. Yeah, Mars has 2 moons, which are very small, are very likely asteroids, which were captured by Mars. They're like, Phobos is about 7 miles in diameter, and Deimos is only about 3 or 4 miles in diameter. And these were partial eclipses of the sun when viewed from the surface of Mars. And the reason that they're doing this is that by precisely timing, oh, and by the way, the Opportunity rover that's been there since 2004 could also observe these partial eclipses. And by very precise timing of these different observations, they can actually use these observations to tell them something about the interior of Mars. Because Mars does respond to the tidal forces of these moons, and so they can get a better idea of how solid or liquid the interior of Mars may be. And they also have described that the orbit of Phobos, which is only 8 hours, so it's very close to the surface of Mars. It's an 8-hour orbit. It's slowing down, while the orbit of Deimos is increasing. That's about 30 hours right now. So eventually, Phobos will probably come so close to Mars that it will break up. And there may actually be a period of time in 10 or 15 years when Mars has a ring around it before this actually crashes into the surface of Mars. So none of these things are fixed systems. They are dynamic and they are changing. So that was one of the things which the rover accomplished and is going to be moving on very soon to Glen Elg. So, okay, now in terms of, I don't know if I'm going to use the projector anymore. In terms of other things which have happened relevant to this is another asteroid hit Jupiter. I had described how Shoemaker-Levy, which may have been a comet, had hit Jupiter back in 1994, and there was a smaller one which hit just last year. And then this week, I think it was September 10th, an asteroid hit Jupiter, and the only reason we knew it was some amateur astronomer with about a 12-inch telescope happened to be looking at Jupiter, and he saw this little flash of light, which actually was captured on video, and they determined, yes, that something had hit Jupiter. This was not something that had been detected. There was no trajectory for this. There was no forecast that this was going to hit Jupiter. It just hit. And it may be that Jupiter, because it has a large mass, tends to sweep up a certain amount of these asteroids, these rocks, and may give us some protection in that regard. The second thing which happened is that we produced a report called The Strategic Defense of Earth, which is available on the LPAC website. We made a couple copies of this, which are back at the literature table, which goes through this whole issue in great detail, including the link to the Strategic Defense Initiative, which LaRouche pioneered back in the late 70s, early 80s. And two of the authors of this report, Jason Ross and Ben Deniston, just spoke, I think on September 3rd through 5th, at an international conference held in Ukraine, which was entitled Space and Global Security of Humanity. And this is something that we had discussed previously, that the Russians have made very important efforts to draw the United States into cooperation on both terrestrial dangers like earthquakes, as well as space threats like astronauts, and we've discussed that before. So there is now an international organization, this is called Ignaz, the International Global Monitoring Aerospace System, with the intention of, I mean, this has been Lynn's idea, and he's been very intimately involved in the creation of this, to bring together scientists from around the world to seriously address these problems. And that, as you'll see, they're all interconnected. The question of being able to forecast earthquakes involves completely different techniques, monitoring things, influences from outside the Earth, rather than simply looking at it as tectonic plates that are somehow slipping, and that's the only factor involved in earthquakes. It's just not true. And it's creating quite a revolution in science in that field. The same will go for asteroid defense, which is what I wanted to follow up on in terms of what's going to be required and some of the revolution in scientific thinking that's going to be required. And this is going to be very, very interesting. As with all problems, they create great opportunities. So there's a positive side to all these threats. So what do we need to do? What kind of economy do we need to create in order to deal with these threats posed by asteroids? Well, one thing, we need to know what's actually out there. And how would we do that? Well, we need some very big telescopes, both on Earth and in space. Now, does anybody know how large the largest ground-based telescope is? It's about 10 meters, a little over 30 feet in diameter, is the largest telescope, visible light telescope. There's a radio telescope in Puerto Rico that's about 1,000 feet in diameter, which is sort of a metal mesh dish built into a little valley that can listen to radio signals. But in terms of visible light, it's a little over 30 feet. Well, there are proposals already for building mirrors substantially larger than that, and we're talking about maybe you would need telescopes that are 25, 50, 75 meters in diameter, which completely dwarfs anything that we have now or are capable of building now. Now, those would be pretty hard to put into space. The Hubble Space Telescope, which has done fantastic work, is 2.4 meters. It's like 8 feet in diameter. And the James Webb Telescope, sort of the next generation telescope, is about 6.5 meters. So they're much smaller, but because they don't have the atmosphere, they can see as well as one of these 10-meter telescopes on the Earth. But you would need to do that in terms of trying to eliminate a lot more of the unknown here, as we described, particularly when you get down to the smaller sized rocks, the 10 meters, 30 meters. which can still do enormous damage if they actually hit the Earth, that 90% of those, we have no idea where they are. So you not only have to be able to find them, but you have to be able to determine where they're going, where they're moving. And that's going to get into a whole nother area of this. Now, one of the things in terms of a space-based telescope is that if you put one closer in toward the sun, maybe not on Mars, maybe we would want to do things on Mars, but if you could put one in closer to the sun, it actually has a wider field of view, because you can't see anything if you're looking in the vicinity of the sun. But if you get close to the sun and sort of turn around and look out toward the solar system, you have a wider field of view. So that would be a good place to put space-based telescopes. And then the other question is actually trying to put transmitters on an array of different asteroids so that we can very precisely track their orbits. Both asteroids that we think might be a problem in the future, right? We discussed that there have been asteroids that have come relatively close to the Earth, have come closer to the Earth than the orbit of the Moon, for example, and that repeatedly cross the Earth's orbit. So potentially 10, 20, 100 years from now, maybe the timing is such that they actually intersect the Earth's orbit when we're there. That's sort of the problem. So if we could put transmitters on a variety of different of these asteroids, we could follow their orbits more precisely, and also try to gain a better understanding of how these different sort of classes of objects behave. Because there's a real limitation to trying to, develop a computer that somehow keeps track of, let's say, 500,000 rocks simultaneously. And something that I want to get to sort of at the end is how this is going to directly challenge our understanding of the whole principle of gravitation. So stay tuned for that. Now, if we determined that an asteroid that we had been able to identify and had been able to determine an orbit for, that we determined that there was, say, a 20% chance that it was going to hit the Earth in 20 years, what would we do? Huh? Well, okay, well, let's say we would want to keep track of it for sure, but we don't just want to say, have a countdown clock that says the world will end and, So what would we do to try to get rid of it?
Send up something, well, maybe a drone.
A drone? Well, we'll put it on Obama's list. Deflect it. Okay, now how might we do that?
Missile?
Some of our nuclear products, like a bomb. So would we try to blow it up?
No, pieces would hit, small pieces would hit the Earth.
If you just break it up into small pieces, that could do as much or maybe worse damage if you have 100 small pieces, right? Yeah?
Set off an explosive maybe near it,
To point
enough
direction,
to move
another
it,
direction.
so that all the changes.
So maybe you could put a bomb nearby that would have the effect of moving it.
Yeah.
Okay.
Glass, move it over.
Okay. That's certainly a possibility. What else? What if nuclear power is completely banned?
Talking on Mars, they're hitting rocks and making it into dust.
With a laser?
With a laser.
A laser, something like that. Okay. Okay. And it is true that if you vaporize a little bit of rock, that the vapor, for the vapor to go this way, it's pushing against something in the opposite direction, so that it does create a tiny thrust. That the vapor, the vaporization of the rock, creates a certain push on the rock. So if you had, would have to be a big laser, but a large laser, given enough time, right? Let's say you had some craft up there that was 100 miles off the surface of this rock and was able to shoot this laser at it for 10 years, right? That might create enough push to deflect it, right?
Well, why would you want to do that for 10 years when you wouldn't just get rid of it?
Well, but the question is, can you get rid of it?
Well, if you vaporize it, you do if you turn it.
Well, that assumes you have a laser that could vaporize, you know, a million tons of rock. So okay, all right, okay, so other ideas. We have a laser that might vaporize it or might just give it a push. A nuclear bomb that also give it a push. What else? Yeah.
Ion engine thrusters on the surface of this thing.
Essentially strap rockets onto the rock and have that push on it. Now, what if this rock is sort of tumbling through space? What would happen with the rocket? Well, it might be pushing it in this direction one day and pushing it in the other direction the other day. So you might have to put a whole bunch of rockets on it that can somehow talk to each other so that they work together to push it all in one direction, right? There's also the idea, this is kind of an interesting idea, they call it a gravity tractor. That in the same way that the moon, or the same way that the Earth, in some fashion, seems to want to pull this piece of paper down toward it, that if I put a spacecraft close to a rock, it will tend to attract the rock, like a magnet. And in fact, if it were, some of these meteorites that you see are largely nickel and iron. So you might even be able to use a magnet. And without even touching it, you could influence its trajectory. Now, the key sort of principle here is energy flux density, which I know we've discussed. Anybody want to tell me what that means? Energy flux density? Come on. After all these classes, the fact that we don't give out homework assignments or give spot quizzes. Okay, well has anyone ever had an operation here? Okay, now, would you prefer a surgeon who had 100 butter knives, 100 butter knives, or a surgeon with one really sharp scalpel? Would you want to have open heart surgery with 100 butter knives? You know, what's the difference? What's superior of a scalpel over a butter knife?
Precise.
Concentrated.
It's precise, it's concentrated. Right? It's a focused form of force or energy, that whatever force you apply to that knife, rather than going on, you know, something as fat as my finger or something, it's going on an extremely thin surface so that it very easily slices. That sort of focusing of energy is what we mean by energy flux density. And the thing that's crucial to understand about it It's not just that you have more of it, which is why 100 butter knives does not equal a scalpel, but that you can do things with that sort of focused, concentrated energy that you could never do with a butter knife. So the thing in terms of, that comes up in terms of this question of asteroids is, well, if all I have is a low power effect, a low energy, let's say it's a rocket, a typical rocket motor that we use to put a rocket into space. Those chemical propellants, if I'm using liquid hydrogen, liquid oxygen, that has actually very low amount of force per weight of fuel. So I can't push very hard. If I have nuclear powered rockets, which we've discussed, if we have fusion energy, which could be applied to provide enormous amounts of thrust, if I have those kinds of concentrated power sources, I can push a lot harder. I can do things that I could never do with a low density power source. Which means that rather than having to design a rocket, detect a rock, design a rocket, plan a mission, get there, and then push for 50 years, well, that's not really going to work very well if we discover it 3 months before it's going to hit. So if we have advanced energy technologies, it means that we can intercept it closer to the Earth. And we can exert a greater force in a shorter amount of time, right? So that the kind of energy source that we have available may very well be a life and death question for whether we can do anything if we do detect an asteroid that is heading for Earth. So it directly connects with everything we've said about the domestic economy, the need for fusion energy. And it also addresses the question of economic infrastructure. Because to really do this right, you can begin to get a sense that you have to have a multi-layered approach to this, much as we did with the SDI. That you're going to need ground-based detection, you're going to need space detection, you're going to need the ability to, on a routine basis, send spacecraft quickly to places all over the solar system. Half of the missions when we go out to Jupiter, the spacecraft, because it's essentially just coasting after it initially gets out of Earth orbit, you send it around Mars and it gets a little kick, and then it comes back and it goes around Earth, and then it goes, they have these incredibly elaborate trajectories to take advantage of this gravity boost you get by flying past another planet, but it takes a really long time. So again, if you have nuclear fission or fusion, nuclear propulsion, you can just more directly go where you got to go, or go to places where you couldn't necessarily sort of hitch a ride on these other planets. They may not be lined up in order to get you where you need to go. So that all of these things require an infrastructure which involves really developing, James Webb called it total space capability. This would include having lunar base on the Mars, having things in Earth orbit, and Moon orbit, and Mars orbit. All these different components will play an important part. And you develop the infrastructure along the way. And it's relevant to think about while shipping goods by water, ocean travel, say from China to the West Coast, is very cheap and efficient for bulk goods. You don't develop anything along the way. If you go out in the middle of the Pacific, there's no cities that have been created. There's not even a rest stop in the middle of the Pacific. that all of this transport has done nothing to develop things in between. You compare that to the railroads, where the very fact that you built a transcontinental railroad didn't simply mean that you could transfer, you know, a box of horseshoes from San Francisco to New York, but cities, industries, farms, everything developed every step along the way. And that the infrastructure, therefore, defines the potential for development throughout that region where it's being built. So that the potential, if you're talking about Mars or something like that, the potential for development at every point in between becomes crucial and becomes an integral part of it. Now, the thing that I want to finish with is there's a section of the report which I hope people will read. We actually covered a fair amount of material in here in terms of the size of asteroids, things like that. There's a section in here called The Solar System from Kepler to Gauss. This is on page 57. It's an appendix. Oh, yeah, this is the Strategic Defense of Earth report. Right. This has not been printed yet. Hopefully it will. But it's available on the LaRouche PAC website. So you can download it and print it from there or read it there. But this gets into one of the most interesting sort of scientific aspects of all of this work, which is that these asteroids, these rocks of varying sizes, don't exactly behave the way that a planet does. And even in Kepler's day, he recognized that the planets did not follow perfect elliptical orbits. And the way that these asteroids are currently tracked is somebody taking a picture in the sky, sees a dot that's not supposed to be there. Wasn't there last month. And on the basis of a certain number of observations, they'll determine, okay, this is something that we don't have in our catalog of satellites, asteroids, stars, whatever. And so it gets a new designation, and they then try to compute an orbit. And the way that they do that is they initially assume that it follows a perfectly elliptical orbit and try to determine what they call the orbital elements. You know, what's its closest distance from the sun, its furthest distance, determine the axis of that and how it's tilted, and all these different parameters that would describe the orbit that this asteroid is following. And that's not terribly precise. It certainly is not precise if you're trying to project this decades into the future to determine, is this going to cross our path within the 8,000 miles, which is the diameter of Earth. If it crosses our path, you know, 50,000 miles from the center of the Earth, we're okay. If it's 3,000 miles from the center of the Earth, we might be dead. So trying to determine that accuracy on a scale of millions or billions of miles is not within our capability at this point. But the other thing that this brings up very directly is, and I know we've had some classes, we've had discussions on Kepler's theory of planetary motion. I'm not going to try to go through that today. But what do people currently think is determining the motion of any of these asteroids, any of these rocks floating in space? What's determining its path?
It could be gravity between the planets.
It could be gravity between the planets?
Or as it gets near to a planet, that planet's gravity could deflect it, you know, to go in a different direction. It
Okay.
doesn't have to necessarily enter into the atmosphere of that planet, but
Okay. All right, but gravity. So you're saying gravitational attraction by another planet. Okay, by a planet. Okay.
In our solar system, it's primarily Jupiter and Saturn that determines some of the stuff. Also the sun. The sun's the biggest actor in the whole system. And that makes more determination than Earth does.
And how does it determine the path?
Well, we're talking about an asteroid that, let's say, it comes out of the asteroid belt. Because of the movement in the belts, some of the random movement will push one of the objects out.
Okay, but I'm saying, how does the sun,
Now it will be affected by the sun's gravity.
how is it affected by the sun's gravity? What is gravity?
Now that's a new push.
A pull. A pull of what to what?
well, it's between two objects.
A pull between two objects.
Maybe three objects.
Maybe three, okay. Well, there certainly could be multiple objects, and there are in the solar system. But are we agreed that gravity is basically a pull between objects? Anyone disagree? What? Speak up.
At some time, it was determined to be a distortion of the time-space continuum.
Okay.
That was the equivalent kind of sync. Took a large piece of rubber sheet, for example,
Right.
and you put a big rock in the middle, and you threw a little small baseball, go to the goddamn and it start spinning around. There was no friction and no loss. It would just keep spinning around and around.
Okay.
Got into that lower end.
Do people really buy that? That somehow our solar system has a big hole in the middle and that's why things fall into the middle? Do people buy that, or do they think it's just the sun sort of pulling on stuff? Huh? Some unnamed person says they think it's the sun pulling on stuff. Yeah.
This, well, the Kepler viewpoint is...
All right. Okay. Don't say it yet. Well, not yet. Okay. The point I wanted to get at, and I'm deliberately trying to set you up, okay, if you hadn't known that, is that everybody here has been brainwashed your whole life into believing that there's this gravitational force, this attraction between two objects that occurs through empty space instantaneously in a straight line. That when I hold this up here, that the Earth pulled it down. Okay? And even though I just told you that I just set you up to say that, you still believe it.
We just saw it.
Yeah, right. We just saw it. You want to see it again? In case anybody, yeah, that's right. Now pay attention. It's going to happen fast. Here we go. Okay? Now, just hang on.
I know what you're talking, I understand what you're saying now.
Yeah, well, but see, this is you've heard us say this before, but that's not how you think. And that's okay, but that's not yeah. What did you want to say, Rich?
If you go to the Einstein view of gravitation,
geometric formulation will seem to indicate, some headed towards it. Another example is when in verification of light, which has mass, bends when it goes to a gravitational object. So what does it mean to be straight? How do you define straight?
Yeah. Those are relevant points. The key thing I want to bring up about Kepler is he's saying there is no sort of mechanical explanation for the path of these planets. That the path of the planets, the ordering, the construction of the planets can only be understood from the standpoint of how the human mind works. That there's a conception of the solar system. It's not sort of just whatever happened to happen happened. That there has to be a conception, there has to be a harmony between the relationships that define where the planets are and how they move. Not only in terms of their distances, but their speeds, and in terms of the way in which their speeds and distances change. That there are relationships between those planets that must be harmonious. And when I say harmonious, I'm referring specifically to things that the human mind would be able to identify as harmonious, either in terms of musical harmonies or geometrical proportions. And those were the techniques that Kepler used to actually discover gravitation. Isaac Newton did not discover gravitation. I can't tell you how many times I have wished that it was the tree that fell on Newton instead of just the apple. Because, since Newton, who's like 100 years after Kepler, the whole scientific community and the whole scientific, discussion of how the world works has been dominated. There's been just a complete obliteration of the method of Kepler and the replacement of that with this dead, inanimate universe of things attracting things. And it's a very unproductive way of studying the universe. And people like Gauss in the early 1800s, who was the first person to define the orbit of Ceres, the largest of the asteroids, who recognized that the whole method of Newton was wrong. That there's a whole, it's like, for the mathematically inclined, I'll just use one example. A sine curve, a nice continuous sine curve, there is no algebraic equation that can describe that curve. It's like trying to, if you've ever had an Etch-a-Sketch, it worked great if you were going back and forth and up and down. But try to draw a curve, you'd always go, right? And you can make it, you can see this on computers have the same problem. If you try to draw a curve, it can only represent it in terms of pixels. It's either down or sideways, so that you can't actually represent a continuous curve. Nicholas of Cusa discussed this in terms of if you try to draw a triangle inside a circle and then a square and then a pentagon, it has more and more sides, and in one way it seems to look more like a circle. It has more and more corners. So in that sense, it's getting further and further away from a circle which has no corners. So that there's a conceptual level where you have to get up above the sort of mechanical, mathematical representation of these processes. And that's what Kepler did. He said, no. We're not going to start by talking about two rocks in space. He does describe that they would be drawn toward each other, but he's saying that there's a more fundamental concept which organizes the whole solar system and the whole physical universe. These are the thoughts of God that he sought to discover in terms of trying to understand the physical universe. And so in the attempt to investigate asteroids, this immediately is brought up because Newton gave up on science and wound up being an accountant. You know, he went to become the mint, running the mint, the exchequer. Yeah, simply trying to give a two-body attraction solution to the orbit of the moon. I mean, what could be simpler? It's real close. We can get excellent observations. It's just us and the moon pretty much by ourselves. He could not do it because immediately you do have these small effects caused by other bodies, and this became known as the three-body problem. That even when you deal with three bodies in space, because they are continuously changing the path of the other bodies, and that one in turn changing the one that just changed it, that the mathematics immediately blows up. When you're talking about asteroids, when we have maybe 500,000 of these, which could actually bang into each other, but there's going to be other effects of whatever impulse that one simply passing, whether it's passing by a planet or just traveling together in a group, these are things which are going to require a higher mathematics and is going to require a return to the conceptual approach of Kepler and Gauss, which is what's so fascinating about this, as opposed to simply viewing it as a real headache. You know, we're going to think of all the computers, you know, servers and hard drives we're going to have to keep track of all these rocks, that it's going to require a rethinking of how we explain gravity, the attraction of objects, all of these things. And well, go ahead, ask you a question before you get a shoulder, something.
Not a question. I was just going to say, although it looks like that piece of paper fell straight, because of the motion of the planet, which is occurring right now, as we're here, that actually fell at an angle.
So do we be hanging onto the wall or something? Yes, that's true, but that's off point. That's off point. That's off point. So the last thing I want to discuss is how much of the universe do you think we understand? On a scale of 1 to 100. And I'm just talking physics. I don't mean understanding why your neighbor, you know, parks his car the way he does. But in terms of physics, in terms of just dead rocks and things, how much of the universe can we see? Well, I don't know. They say that we can see galaxies that are over 13 billion light years away. They just discovered one that they think they're looking at it when it was only 500 million years old.
Can't see any.
Huh?
Can't see any.
Can't see any.
No, because it's like trying to discover. You take a mass like a marble, and you take a mass like the Earth. If you live forever, you'll never find out all the intricacy of that marble in comparison to the Earth.
Okay. Well, let me. Maybe I should ask it differently. Have people have heard of the Big Bang theory, right? That supposedly 13.7 billion years ago, the entire universe was the size of a BB or something like that. And yeah, popcorn kernel before it popped. And when that one popped, it really popped. And the current theory of cosmology is that after the point of the Big Bang, the universe has just expanded from there, right? So that everything is moving away from everything. Okay. Now, if in fact everything is simply being attracted to everything else, according to our theory of gravity, what should happen to the rate of expansion of the universe? You'd think it would slow down if there's some kind of a pull. If if I'm pulling everything in towards me, that this initial expansion should slow down and possibly all collapse on itself, or just sort of slow down and stop expanding maybe? What?
I don't know, does dark matter get into this at all?
Yeah, well that's what I'm getting to. The observations, and again these are all subject to lots of questions, the observations are that in fact the expansion of the universe seems to be accelerating. So how can we explain that if everything is attracting everything else? How could it be accelerating the expansion?
Well, there's dark matter and
Well, wait a minute. Don't just give it a label. Don't just give it a label. It could mean a couple things. What you referred to of dark matter is this, well, if things are moving away from each other and faster, there must be something pushing everything apart that we can't see. Okay? And they make estimates on the amount of that, and they design experiments to try to, detect it. And then when that's inadequate, they came up with dark energy, which is even more invisible and even more powerful in terms of expansion of the universe against what gravity should make it do. And the actual numbers on this, just so you know what we don't know, what they currently say is that, I didn't write it down, but that the visible universe, what we think we can see, dust, gas, rocks, planets, is 4% of the universe. Dark matter is about 23%, and whatever's left over, 73%, I think, is this dark energy. Now, I'm only mentioning that to make the following point. Maybe we have been encouraged to come up with these invisible forces, invisible dark energy, invisible dark matter, because our conception of gravitation is flawed. That the way in which matter and energy interact in the universe is not pair-to-pair interaction based on mass. If that were true, if our understanding of gravitation were wrong, then perhaps the way in which we see these observations of the universe are because of that flawed understanding of gravitation, not fairies, fairies pushing atoms apart or something. So,
What about once an object has left the force, there's less resistance. So less resistance, it should then travel further and faster away up to a point.
Well, I mean, there are many things that don't make sense given our current understanding of gravitation. And I don't want to go on further, but when we put out a pamphlet called Planetary Defense before this one, which goes through a lot of the anomalies in terms of the rotation of galaxies and redshifts and all sorts of things, which challenge sort of, mainstream thinking on all of these questions. And I just want to make the point that in terms of trying to understand how these asteroids are going to be traveling and how we're going to have to try to interact with them to avoid, Earth strikes and things like that, this may be a very real opportunity to help crack some of these other problems.
What propels an asteroid to go so fast? And we have to develop something to propel us to go to Mars, and we need some type of fuel or whatever. And these asteroids don't have anything; they just fly through space.
Oh, in fact, you want to hear a really scary thought? You've heard of long period comets? Asteroids are bad enough, but most of them are currently, we sort of at least know they're sort of within the solar system, which gives us a chance of seeing them and starting to track them over time. Some of these comets come in from far, far outside the solar system that may have, if they actually have a repeating orbit, it could be thousands or millions of years, which means we're never going to see it coming. We will never have seen a comet before it comes in close enough to be observed. So there's no potential to determine an orbit over a period of time and say, well, when it comes back in 37 years, where will it be? And the speed of these comets can be 150,000 miles an hour instead of the measly 20 to 40,000 miles an hour that we've been talking about in terms of asteroids that have hit the Earth. So that the energy delivered by one of those comets, they tend to be big also. So this is like, we better get to work on the easy stuff, the asteroids, because if we find out that there's a comet with our name on it, that's a completely different class of problem. Yeah.
Couldn't you say that gravity, in a way, civilized the universe? The universe is civilized in the sense that planets don't crash into other planets. Planets go around stars, and stars go around galaxies, and so on. And this is all the result of gravity. But, of course, there is, as you say, there is the danger of a planet being hit by an asteroid, like our planet. But gravity civilized the universe, and I believe it's the force that's trying to pull the whole universe back since the Big Bang, that caused it to expand.
Well, Kepler conceived of that as the goodness of the Creator. That the Creator made a harmonious and lawful universe that is at the same time beautiful and knowable. So that was how he was able to discover the organizing principle of the solar system. I hate to use the word gravity, even though he discovered it, because people immediately think of, this attracts that. Yeah, and that was not at all his. Everything he did with the planets was done without any idea of mass, which is supposedly integral to the Newtonian equations. It had nothing to do with that. It had nothing to do with the character of the object. It had everything to do with the character of the system as a whole, and what was therefore possible even for the Creator, that he would have to create it in a very specific way. So anyway, I want to stop now because I think we want to have some discussion of organizing and what people are going to do.